Another beautiful example of limit cycle behavior is embodied by something known as the van der Pol oscillator. This model was invented a long time ago to describe electrical oscillations in nonlinear circuits, and it turns out to be a very useful paradigm for all kinds of self-sustained oscillations that are not at all harmonic in time. So let me first write the equation of motion for the van der Pol oscillator. It's x double dot plus mu x squared minus 1 x dot plus x is equal to 0. So it looks like the equation of a damped oscillator, damped harmonic oscillator, but with a damping term that can be changed sign whether or not x squared is larger or less than 1. So for x larger than 1, this would describe normal damping. The sign of the damping term is the same as the acceleration, and it tries to slow down the oscillator. But on the other hand, if x is less than 1, it's negative damping, and it tries to drive the oscillator back to x going to 1. This negative feedback is what gives self-sustained oscillations in this van der Pol oscillator, because the damping term can either be positive, slowing down the oscillator, or negative, speeding it back up again. And the interesting limit we're going to care about is mu much, much greater than 1. Now, as written, this does not look like a dynamical system because it's a second-order equation. But one can map this to a two-dimensional dynamical system because it's a second-order equation. So it's a clever transformation to make it into a two-dimensional dynamical system. Let me just write the answer, and then it's really easy to verify that this is exactly equivalent to the original equation of motion. X dot is equal to mu y minus f of x, where in this equation, f of x is equal to x cubed over 3 minus x. And y dot is equal to minus 1 over mu x. So this is now a two-dimensional dynamical system, and it's easy to verify by taking another derivative with respect to time that these two equations are exactly equivalent to the original one-dimensional equation of motion. So now that we've written this as a two-dimensional equation, let's try and infer the dynamical behavior of the system. And once again, we apply the tools that we've been learning about looking at the null-clines and the behavior near the null-clines. So if I plot in the xy plane, there are two null-clines. One null-cline is just setting x dot equals 0 gives me the null-cline y is equal to f of x. And the null-cline y dot is equal to 0 just gives me that x is equal to 0. So those are our two null-clines. So let's look at these null-clines and look at the flow around the null-clines. So the null-cline x dot equals to 0 is just the cubic curve x cubed over 3 minus x. So it's a cubic curve that looks something like this. So this is a null-cline x dot equals 0. And once again, we can infer the flow on either side of the null-cline. So along the null-cline, the horizontal flow is 0, and to the right of it, horizontal flow is negative, and to the left of it, the horizontal flow is positive. And then we have the other null-cline, which is just the x equals 0, so it's the vertical axis. So this is a null-cline y dot equals 0. And here it's easy to check that the flow is downward to the right of this null-cline and upward to the left of the null-cline. So let's now use this picture to try and infer the flow. And in particular, we're interested in the limit where mu is much, much greater than 1. And notice that if mu is much greater than 1, y dot is generally slow flow because it involves 1 over mu, whereas x dot is typically fast flow because mu is much bigger than 1. So as long as y minus f of x is not close to 0, which is as long as we're not close to the null-cline x dot equals 0, then the flow is going to speed very quickly to the right. So let's try and draw in like a typical trajectory. So let's say we start somewhere here, for example. So in this region, the flow is to the right. The horizontal flow is really fast. The vertical flow is really slow. And so basically we zip around to the null-cline. Now what happens when we reach the null-cline? When we get really close to the null-cline, y minus f of x is sufficiently small that it cancels out the very large value of mu. If you want to look at this more carefully and analytically, there is, when y minus f of x is of the order of 1 over mu squared, then the magnitude of x dot will be mu over mu squared, which matches that of y. And so the flow is both of order 1 over mu in both x and y. So when I'm very close to here, the flow in both the horizontal and vertical directions are roughly the same order of magnitude. what happens is you just overshoot a little bit. And now if you overshoot a little bit, the flow is to the left, but it's also downward. And they're both happening at roughly the same speed. So one just follows along the null line just to one side of it until one reaches here. And then down here, the horizontal flow is again very fast. So we zip over here and do the same thing as what we did when we first hit the null line. We just overshoot a little bit. And now we go upward until we hit this hump, and then we zip over here, and then we just repeat the cycle over and over again. So this is the self-sustained oscillations that occur in this van der Pol oscillator. And some important features are the fact that there is these two different time scales buried into this equation, so that there's very fast flow in the horizontal direction, very slow flow in the vertical direction. The other feature is that one needs a cubic nullcline, and the interaction of a cubic nullcline with more or less a much more slowly varying or linear nullcline is what allows these self-sustained oscillations to occur.